We're going to try and complete this topic probably, hopefully, in this class, idle gases. The first thing about idle gases is that it's a very small topic actually. It's a model for gases, and and it's a model of what a gas should behave like. Okay, so it applies to all gases, but not all gases are ideal gases. Uh, Most of the gases they behave very similarly, but there are differences as well. So this model is an approximation. It applies to all gases, but it doesn't really model them all of them as correctly as possible. So the first thing is we need to describe what a model of an ideal gas is going to be looking like. When you think of a gas, let's say there's a container, and whenever you think of gas molecules, you think of gas particles as being really far away from each other. Tiki, you have studied this in O levels kinetic particle theory. So you think of gas molecules as being very far away from each other and randomly traveling in all directions. They don't have one direction, they're all randomly bumping and bouncing off each other and with the walls of the container, and they all have different speeds. So, this is how you imagine a gas to be. So, there are two main assumptions when you think of a gas. uh, when you think of it as being different from what a liquid or a solid is. So the main assumptions are number one, that that intermolecular forces are negligible. Now, in liquids and solids, the intermolecular forces are not negligible. The particles are held tightly together. So intermolecular forces are not negligible, but for gases, intermolecular forces are considered to be negligible. What that means is, and that's very obvious, what that means is that if this particle is traveling, the other particles are not going to be attracting it, which is why it's freely moving in all directions. That's the number one reason why. So if these two particles, they don't really attract each other much. Similarly, these two particles, they don't attract each other much. So gas particles don't really like to attract each other. They have negligible intermolecular forces. And the second assumption is that volume occupied by the gas particles are negligible by gas particles are negligible compared to the total volume occupied by the gas. So, what does this statement mean? That's the second assumption, but what does it mean? What it means is that a gas would be occupying a very large amount of volume. So, for example, if you look over here, this gas is occupying the entire container. Uh, so it's occupying a large volume. So gases occupy a very large volume because there are large gaps in between. But the gas particles themselves have negligible volume. What that means is that if you look at the gas particles, then most of the volume is empty spaces. The gas particles themselves, if you pick up all these gas particles and you put it in one corner, then the gas particles are not going to be occupying a large volume. So the gas particles themselves have negligible volume. but the total volume that they occupy, it involves uh, empty spaces. So most of it is just empty spaces. So what that simply means is, what this assumption simply means is that there are large gaps between gas particles. So the volume total that's being occupied, that's going to be very large for any gas. But in reality, the particles themselves would have negligible volume. So most of it is just empty spaces in between the particles. So this is what is meant by the second assumption. Okay, so and let me highlight the second assumption more clearly as well. Like if I pick all these, somehow if I end up picking all these particles up and I put them together, then the volume of these particles is almost non-existent, right? So the particles themselves almost have no volume. It's just that they occupy a very large volume because they are spread out, and they usually fill up any space that you put them into. So so whenever you see a gas, it's mostly empty spaces. So these are the two main assumptions, and there are other assumptions as well. The other assumptions are, now these are the lesser assumptions. You'll mostly be asked about the two main assumptions. The other assumptions are that temperature of a gas is proportional to kinetic energy of the particles. So when you measure temperature of a gas, you're basically measuring the average kinetic energy, and this is the average kinetic energy we're talking about, because not all gas particles are going to have exactly the same energy. They're all bumping with each other with the walls of the container. So some would have more energy, some would have less energy. The second point is uh, that all collisions are elastic. And particles behave as rigid spheres. As rigid spheres. What that means is that when these particles are bumping into each other, uh, they're not losing energy or gaining energy. Overall, the collisions are elastic, which means that kinetic energy is not lost. Uh, if one particle gains energy, the other one probably loses energy, so the net total amount of energy remains constant. So that is what is meant by elastic collisions. Then we can come up with a third point. We've actually written down the third point, that they do behave as rigid spheres, so that's done as well. So these are some of the other assumptions. But these are the first two are the main assumption. Is this clear? Yes or no, Rida? Sanjita, is this clear? Now, now the thing is, these two assumptions. Now the thing is, these two assumptions, they're not always true. For example, the first one, intermolecular forces are negligible. That is true to an extent, but it's usually truer at higher temperature. I mean, if a gas is at higher temperature, then the intermolecular forces are definitely going to be negligible. Like, For example, if this particle is really, really energetic and it's quickly moving around, then the intermolecular forces, it won't really matter if the other particles attract it or not, because it would have so much energy that it would easily overcome those uh, uh, intermolecular forces. So the first assumption is going to be truer at higher temperature. So a particular substance is going to behave as a gas at higher temperature. Any substance would probably appear to be behaving as a gas at higher temperature. For example, if you take H2O, if you take a water molecules, water molecules are going to behave more like a gas at higher temperatures. Why? Because at higher temperatures, the particles would be so energetic that they would overcome the intermolecular forces and they would start moving in all directions freely, like a gas. So, so this first assumption is truer at higher temperatures. At lower temperatures, intermolecular forces relatively become more dominant. Why? Because the particles don't have energy to overcome those intermolecular forces. So, for example, water is not going to be behaving as a gas at lower temperatures. At lower temperatures, it would probably be behaving as a liquid or a solid. So, the first assumption is more correct at higher temperatures. And what about the second assumption? The second assumption, the second assumption is that the second assumption simply is that gases have these wide gaps in between. Okay, that's what the second point means. And the second assumption is actually truer at low pressures. Because at low pressures, let me draw a container with a piston. Okay, so there's this container with a piston, and there are gas particles in it, and the gas particles are far away from each other. So at low pressures, this assumption is definitely true. If you take the same container to a higher pressure, and by higher pressure we mean we're trying to compress the gas. So if there are gas particles and we push the piston down, we compress it, then that would mean that all the gas particles, they would become really tightly packed. They would become close to each other. And I'm pushing it downwards. So this is higher pressure. So at higher pressure, a gas is less likely to behave as a gas. Why? Because the particles would be really close together, and if they're really close together, they would probably be in liquid or solid state. I mean, imagine that you have used such a high pressure that all the particles are really close together and tightly packed. So when they're tightly packed, they can't move freely. And let's assume that you're using such a high pressure that all particles, they have become they've squeezed together and they've become completely tightly packed. So they appear to be behaving as solids then, because the particles would not be able to move around. There wouldn't be any gas between particles, and uh, they would be vibrating from side to side. Not do they would basically be behaving as solids. So to behave as a gas, the particles need to be really far away from each other, and that's only possible at low pressures. Like if you keep the piston, if you keep the volume large. So this is low pressure. So any gas would, this second assumption would only be true for gases if the gas is at low pressure. So most gases, is the second point clear to everyone? Yes or no? Achha, so based on this, what we have is that based on this, what we have is that any gas approaches ideal gas behavior, or appears to behave like a gas under two conditions. So any gas approaches ideal gas behavior if or under at low pressures and high temperatures. So these are the two reasons, and you will be asked about these two conditions. So any substance probably behaves as a gas if the pressure is kept low and the temperature is kept very high. Okay, take the example of water. If you keep the pressure really low and if you keep the temperature really high, it's going to behave as a gas. So these are the two main assumptions. Now, one second, let me. Now, based on this, now we know what an ideal gas is. There are a couple of things. There are graphs which you already studied in O levels physics. The first relationship is that pressure and volume are inversely proportional for a gas. Uh, you increase pressure, volume decreases, and vice versa. So that's the first relationship, that pressure and volume are inversely proportional. Now, this relationship, what does that mean? It means, let me draw the piston again. Uh, so, yes, exactly. When I talk about a relationship, I'm basically whenever I state a relationship, assume that all the other factors are constant. Every other factor is constant. Okay? It's just a relationship between pressure and volume. So not only just temperature, number of moles, etc., of the gas, every other variable is a constant at the moment. So pressure is inversely proportional to volume. So it's pretty obvious that if you have a gas and you increase pressure, then the volume would decrease. Okay, so that makes perfect sense. So keep on increasing pressure, the volume keeps on decreasing. So they are inversely proportional. But there's a problem with that, and that problem is that this relationship. Remember, all gases are not ideal gases. I mean, I told you that ideal gas behavior was only possible at low pressures and high temperatures. I said, so what's going to happen? This relationship fails. I mean, you need to know the limitation of the relationship as well. It's not that you all keep on increasing pressure and the volume keeps on decreasing. The relationship fails at high pressures. At high pressure, this relationship doesn't work. Why doesn't it work? Just imagine that you're trying to compress a gas. So if you're trying to compress a gas, the particles are getting closer and closer together. Okay, so the particles are getting closer and closer together. You're increasing pressure and the volume keeps on decreasing. But up to a certain point, like the piston would move downwards, but up to a certain point, there would come a point where the gas particles are so tightly or they're so tightly packed together because of the high pressure that you're using, you're trying to compress it, that they're no longer going to compress. Gases can only compress to a certain point. Beyond that point, the volume would not decrease. So relationship fails at high pressure. At very high pressure, so what happens at very high pressure? Uh, Volume would not decrease. I mean, the volume would only decrease as long as there are gaps between the particles. Okay? If you reach a very high pressure and you have removed all the gaps between the gas particles, then beyond that, the volume would not decrease. So the gas would become incompressible. So volume would not decrease as gas particles no longer have gaps in between them. Now the relationship, the ideal gas relationship assumed that the volume would go to zero. If you go to if you keep on increasing pressure, if you go to infinity, if you take the pressure to a really high amount, the volume should decrease to zero because the ideal gas assumed that the particles themselves had negligible volume, when in fact they do have some volume. At the end of the day, you'll be stuck with that. The piston would not move beyond a certain point because the particles have some volume. So the second assumption that we had, it's going to fail at high pressures. I mean, which we already discussed over here. That volume occupied by gas particles are negligible. That is true. That is true if there are large gaps in between. Uh, but once you have removed all the gaps, then this assumption really doesn't has failed, and it's no longer going to be true. So at very high pressure, volume would not decrease as gas particles no longer have gaps in between. So the second assumption becomes fails at high pressures as gas particles don't have negligible volume. So assumption number two fails at high pressures as gas particles don't have uh, I mean, previously we said they had negligible volume, but now uh, their volume is no longer negligible. So the volume, according to this, should have gone to zero, but it's not going to go to zero. Okay, is this point clear to everyone? That this is a relationship, it works fine as long as you don't go to very high pressures. Okay, so any ideal gas, this relationship works very fine as long as you don't go to very high pressures. And the second one, the second relationship is that pressure is, I mean, this is one, pressure is inversely proportional to volume. Then you have pressure is directly proportional to temperature. Again, I'm assuming that all the other factors are completely constant. Now, pressure is directly proportional to temperature. It makes perfect sense that if you have a container and if the gas particles have more temperature, more kinetic energy, then they're going to go and hit and collide with the walls of the container more frequently and more effectively as well. So they're obviously going to exert a greater pressure. So we can explain that higher temperature. So your particles have more kinetic energy. So particles have more kinetic energy. So more frequent and forceful collisions or effective collisions with the walls of the container. So it's a fairly it's a fair relationship. Pressure is directly proportional to temperature. But even with this relationship, remember this relationship is also going to be affected because it's not really going to work at low temperature. The relationship doesn't work perfectly at low temperatures. So why doesn't it work at low temperatures? The reason is that at high temperatures, intermolecular forces are negligible. I mean, if they are very energetic particles, so they don't really care. Like if this particle is moving, it doesn't really matter. The intermolecular forces don't really matter. If it's moving, if it's very energetic, it's going to go and bounce off the container and hit the container with a lot of force. But if the particles have very low energy, then the intermolecular forces they become more dominant. What that means is that the particles they start to attract each other. I mean, they were already attracting each other, but now they're more dominant. Why? Because the particles you're at lower temperature. At lower temperature, so at lower temperatures, the intermolecular forces, the particles will not be able to break free of the intermolecular forces. So all these particles they would be attracting each other, and they would be attracting each other, and they would be slowing each other down. Imagine that this particle is trying to go and hit the wall of the container. So try and imagine that this particle is sorry. So try and imagine that this particle over here is trying to go and hit the wall of the container. Now, if it's trying to hit the wall of the container, the other particles, and this particle does not have enough kinetic energy, it's at low temperature. So that means this particle is not able to overcome the intermolecular forces. The other particles are pulling it back. So if the other particles are pulling it back, it's going to slow down. So this particle over here would slow down. It slows down because of the intermolecular forces of the other particles. So because of intermolecular forces or attractive forces of the other particles. So overall, the particles are not going to bump into the container that strongly. So a lower pressure, so actual pressure would be lower. So in reality, the pressure that you're going to be measuring would be much lower compared to this relationship. So the relationship suggests that if you decrease temperature, the pressure should decrease proportionally. But that's not going to happen. If you decrease temperature, the intermolecular forces, they become more dominant, and the pressure that the particles should have exerted, that's going to be lesser because the particles would be slowing down because of the intermolecular forces. So is this point clear to everyone? Yes or no? Rida, Sanjita, is this clear? TK Yusuf. So, so you had these two relationships which work fine. Pressure is inversely proportional to volume. It's a perfect relationship, except for the fact that this relationship doesn't really work at very high pressures when the gaps are gone. Then, if you increase pressure, the volume would not decrease. And the second relationship, pressure is directly proportional to temperature. It works perfectly as long as you keep the temperature high enough, as long as the intermolecular forces are negligible, or the particles have enough kinetic energy to overcome those intermolecular forces. But this relationship also doesn't really work if the temperature is kept too low. Then what would happen is that the particles would slow down because of the intermolecular forces. All the particles are attracting each other, so they're not going to move away and hit the container that strongly. So the pressure, the actual pressure would be much lower uh, than what you're getting from this relationship. So anyways, you can combine. I mean, there's a third relationship that's fairly obvious. There's no issues with that. Its pressure is directly proportional to moles. So that's, I don't think if that, I mean, there's no way this relationship could actually fail. You have more moles of a particular gas, the pressure would be more because there would be more collisions. So we can combine all of them together into this. That pressure is proportional to moles, it's proportional to temperature, and it's inversely proportional to volume. So you can combine all of them together into this one equation, and what you can do is you can rearrange this. It would be PV is equal to N, add a constant as well, so that you get rid of the proportionality sign. R is your constant, that's known as a gas constant. So combining all these relationships, you can come up with this relationship, which is PV is equal to nRT. And what you need to remember about this is that pressure should always be taken in pascals. Volume should, when you're using this equation, should always be in meter cube. N is moles. R is your gas constant. And the value is 8.31. And temperature should always be in kelvins. So if you're given centigrade, it's going to be plus 273. You'll get kelvins. So you have to be very careful with the units. Meter cube, I'll talk about the conversion of like if there's cm cube, you want to convert to dm cube, you want to convert it into meter cube. That's all divided by 1000. So remember these conversions. So next class we're going to talk about, we're going to try and do questions on this. Okay, so is everything clear? Yes or no? Is everything clear? Chalo, theek hai. We'll continue with this in the next class tomorrow then, inshallah. Okay, take care. Allah Hafiz.